Hello, my name is Jeff Morrison. I'm the program manager for SAFESEE, a NAVAIR program being performed at Scientific Systems Company. SAFESEE is a collision threat detection solution applied to unmanned aircraft systems such as the Navy MQ-8C Fire Scout. SSCI prides itself in developing autonomous systems across a variety of domains. We are a small business located outside of Boston, Massachusetts, focusing on research and development using advanced perception, decision logic, and machine learning algorithms to solve some of our country's most challenging autonomy-related technical problems. Our solutions have been applied to land-based autonomy, unmanned aerial vehicles, maritime systems, including underwater and surface vehicles, and we have a payload on orbit as we speak for a collaborative space-based autonomy mission. Our development in collaborative mission autonomy is applicable across multiple domains. Our first technology breakthrough that resulted in field testing of a large network of autonomous vehicles was in the maritime systems domain under the DARPA CNAV program in 2008. Since that early work on collaborative network of autonomous underwater vehicles, we have expanded our focus areas from feedback control, sensors and signal processing, innovative algorithm development, and networking into the broader realm of a collaborative mission autonomy architecture that is being applied and fielded successfully for drone missions, swarm and satellite missions, terrestrial autonomy, and maritime applications. SSCI approach to autonomy brings a continuous maturation from basic core autonomy through intelligent cognitive mission autonomy, where the agent is no longer just performing mundane tasks, such as waypoint control, or assisting in mission planning, such as solving for optimal search patterns. Instead, it has been designed to work as part of a team composed of human and autonomous agents, seeking to understand mission objectives and reacting to real-time commander's intent. With fully autonomous situational awareness, dynamic decision-making, and multi-vehicle control, the autonomy enables AI/ML, adversarial reasoning, learning, and prediction for an overall improvement in mission effectiveness. SSCI has had programs enabling each of these levels of autonomy, and we are pushing the envelope to increase our TRL at every functional level. The Navy challenge is to be able to acquire a common framework that addresses the core safety challenges associated with the autonomous operation of military unmanned aircraft systems. This common framework should combine an advanced suite of software modules with low size, weight, power, and cost hardware to provide safe launch and recovery, sense and avoid, GPS-denied navigation, and mission autonomy capabilities for increased UAS autonomy. Pictured here are the modules developed by SSCI based on engineering collaboration with Northrop Grumman and PMA 266 for the MQ-8C Fire Scout. The upper left component is the production representative SAFESEE basic camera array. Together with software on the processor, pictured lower right, the SAFESEE component provides sense and avoid with technology capable of providing essential collision threat detection and avoidance capabilities in the operational airspace. Also shown are the SSCI-developed INAV-SL camera modules making up the launch and recovery component. These components are all part of the SSCI's OASIS common framework. OASIS stands for Open Autonomy Safety Enhancement System, and here we lay out the growth path to increased levels of autonomy for Navy UAS. INAV-SL is our image-based shipboard landing system, which has flown in a ride-along capacity with the Fire Scout as part of pre-ECP activities. SAFESEE, which I will focus on here today, is our image-based collision threat evaluation system for the MQ-8C and the MQ-25. We have commercially flight tested SAFESEE on a host aircraft with incoming aircraft intruders. We've begun to enhance our I-9SL landing system to support fixed-wing aircraft, such as the MQ-25, and we have performed flight tests simulating carrier landings. We can easily plug in our existing ImageNav non-GPS navigation technology and have plans to integrate manned-unmanned teaming into the OASIS framework. SAFESEE provides essential collision threat detection and avoidance capabilities in the operational airspace using electro-optical and/or infrared sensors. But unlike range-based air-to-air collision detection strategies, SAFESEE characterizes optical time to contact as the time remaining before a perceived threat collides with the host aircraft. In the upper right figure, we depict our modular architecture. SAFESEE image processing components detect and track potential threats as well as validate and assess them. Track management and risk evaluation modules build a list of actual threats with their relative location and time to contact. This information can then inform an avoidance maneuver. The SAFESEE system integrates easily and can act as either an alternative or complementary approach to more traditional collision sensing methodologies such as radar, ADS-B, and others, which may provide cues. Below is a notional figure showing how the MQ-25 could leverage the current OASIS developments for the MQ-8C Fire Scout. Earlier I mentioned our commercial flight testing of SAFESEE. Here are pictures of our prototype SAFESEE payload mounted onto the host R-44 helicopter. Also pictured are the R-44 intruder helicopter, and for a different series of tests, the Cessna Caravan intruder aircraft. Above and below the Cessna are examples of SAFESEE results from both tests, indicating our estimated time to contact. For the Cessna example, SAFESEE declared 100% probability of collision at 59 seconds time to contact if both aircraft stayed on their same trajectory. Our flight tests are carefully choreographed for safety to prevent any incidents. Between flight test events, SSCI improved the software by adding false alarm mitigation, more robust expansion tracking, timing synchronization, and porting automated camera exposure from I-9SL. We also developed the compact hardened production representative SAFESEE basic camera array shown earlier, on which we will perform the same flight tests and assess the results. Here is a more detailed representation of the latest SAFESEE flight test results. This is a single frame from a video of real-time playback at the moment that SAFESEE converged on 100% probability of collision, with the estimated time to contact overlaid on ground truth shown in the lower right. In the lower left is the overhead view of the aircraft positions. The upper left and right show imagery for both the wide and narrow view processing of the intruder's track and expansion. SAFESEE reports the azimuth and elevation of the intruder and the estimated time to contact, which in this case is 59 seconds at 100% probability of collision. We emphasize here two key features of SAFESEE, along with their advantages and benefits. The first key feature is that SAFESEE employs proven strategy via EO and IR sensors and advanced computer vision algorithms. This sensor algorithm combination provides the advantage of directly determining time to contact as the time remaining before a perceived threat collides with the host aircraft. The benefit is that SAFESEE gives autonomous air vehicles the ability to identify aerial collision threats in an operational setting in time to do something about it. The other key feature is that SAFESEE's high-level output is a semantically meaningful characterization of the risk that a tracked threat will collide with the host if both aircraft maintain their current flight trajectories. The advantage is that SAFESEE output includes bearing, time to contact, and imagery of the threat or threat features suitable for a traditional display as shown, with the benefit that the output can be used by either an operator to command avoidance maneuvers or by an autonomous system to generate reactive maneuvers in a timely manner. Our plan to transition to the fleet includes further flight testing of the SAFESEE basic camera array, both commercial flight tests and MQ-8C ride-along testing. However, the basic capability has some known limitations, such as limited field of view, collision warning only with no avoidance advice yet, and a basic interface with the MQ-8C VMC and basic operator user interface. Ongoing at SSCI is the development of the SAFESEE objective capability, including a smart camera array with a much expanded field of view and image processing performed right at the camera module. We're also developing a degraded visibility warning capability into the smart camera array and adding software to incorporate ADS-B as input, provide avoidance advice, and a full operator user interface. Longer term, our plans include developing multi-spectral capability for degraded visibility conditions, a star tracker for non-GPS navigation capability, push-button operator-initiated collision avoidance, and autonomous collision avoidance. Autonomous collision avoidance could potentially come from another SSCI effort, REACT. REACT stands for Robust Encounter Avoidance and Conflict Resolution, and here is applied for unmanned carrier aviation specifically. As an SPR Phase 2 effort, REACT has a method to use time to contact, like that which is determined by SAFESEE, as a trigger to provide estimation, prediction, and optimize maneuver recommendations to reduce the likelihood of loss of separation and eliminate the risk of collision. We appreciate your support and curiosity about our Sense and Avoid solutions, and would love to talk with you more about your own emerging needs for autonomous systems.